one of the theme of the Ifac World Congress this year is automatic control for the benefit of humankind. And our next talk is precisely that. It's the application of engineering to a real-world problem that is affecting many people, and that's the cleanup of the Fukushima Daiichi nuclear plant after the disaster there. And we have a proper expert to talk to us. That's Professor Hajime Asama from the University of Tokyo. I'll just read his biography quickly and then let him get to the stage. Professor Asama received his bachelor's, master's, and Doctor of Engineering degree from the University of Tokyo. And then he worked in the Institute of Physical and Chemical Research and later became professor into artifacts at the Center of Engineering at the University of Tokyo in 2002. And since then has been a professor in the School of Engineering at the University of Tokyo since 2009. He received the Japanese Society of Mechanical Engineers Robotics and Mechatronics Award in 2009 and the Robot Society of Japan Award for Distinguished Service in 2013. He was the Vice President of the Robot Society of Japan from 2011 to 2012 and ADCOM member of the IEEE Robotics and Automation Society from 2007 to 2009 and President-elect of Intelligent Autonomous Systems Society from 2012 and Associate Editor of a number of journals including the Ifac's Control Engineering Practice, Journal of Robotics and Autonomous Systems and the Journal of Field Robotics. He was Director of you're going to have to correct me, Mobiligence, which is emergence of adaptive motor function through body, brain, and environment, a program in the MEX grant in aid scientific research on priority areas from 2005 to 2009. He's a fellow of the Japan Society of Mechanical Engineers and the Robot Society of Japan. And Professor Asama is the task force on the, for the remote control technology of the Council for the Decommissioning of the Fukushima Daiichi nuclear power plant. So it's in that role that we introduce him here. Professor Asama, thank you.
Thank you very much for a kind introduction. Good evening, ladies and gentlemen. I'd like to thank Professor Ian Craig and Professor Edward Boje and organizing committees for inviting me here. It's my great honor to give a plenary talk in this Ifac World Congress. Actually, my background is service robotics or biorobotics, but after the disaster, the Great Eastern Japan earthquake and the accident of Fukushima Daiichi nuclear power plant happened in March 2011, my life was completely changed. And I'm now so much involved in the activities to introduce robot technology or remote controlled machine technologies to the disaster sites. And so today, I don't talk my research, but I'd like to talk how we introduce such kind of technologies to the real sites. And this is the stories. Actually, the movies didn't work, so I don't know why, but okay. The Great Eastern Japan earthquake and tsunami happened in March 11, 2011, and the magnitude was 9.0. I'm sorry. 9.0, and the maximum seismic intensity scale was 7. So this is a seismic center. But after the earthquake, tsunami attacked the area, the eastern coast area of Japan, and 30 or 60 minutes later than the earthquake, and it totally destroyed these areas. And the biggest issue was this tsunami attacked also the nuclear power plants in Fukushima. And this is a scenario of the accident happened in this nuclear power plant. So after the earthquake, once the power supply was lost, but the emergency generator was activated, and the scrum was successfully done, and the reactors are stopped. But after that, the tsunami attacked this nuclear power plant, and this is the location of the Fukushima Daiichi nuclear power plant. And all the fuel tanks and generators were damaged, and finally, situation blackout happened 1 hour after the earthquake. And then a cooling system of reactors and fuel storage pool became in failure, and cooling water was lost, and it is considered that all the nuclear fuels melted down. And another biggest issue was the hydrogen explosion. For the unit 134, the hydrogen explosion happened, and very huge amount of contaminated materials are released from this nuclear power plant. And this is a list of accidents of nuclear facilities. 3 Mile Island accident happened in 1979, and it was a level 5 accident. It is accident of coolant loss. And the Chernobyl accident happened in 1986. The level was 7. In Japan, there was a critical accident of fuel processing in Tokai, happened in 1999. It was the biggest nuclear accident before we had Fukushima accident. And several people are killed by this accident. In the case of Fukushima, level was 7, even if there are nobody were killed by this accident. And in Fukushima Daiichi nuclear power plant, we had 6 units, and unit 1, 2, 3 was under operation, and 4, 5, 6 were under maintenance. And this is the north side. There are 5 and 6 in north side, and this is the sea side. Its direction is this side. And these are some photos of the buildings. By the hydrogen explosion, unit 1, 3, 4, the reactor buildings were totally damaged. And even in unit 2, the hydrogen explosion did not happen, but there are lots of contaminated materials also released from this unit. And this is a rather recent photo, which is taken in 2013, February. And this is Unit 1. Unit 1 is now covered by this kind of coverage. This is Unit 2. And Unit 3, there are some debris on the operation floor, but it is now, it was already removed by this kind of crane or construction machines. And this is Unit 4. And Unit 4 is under extraction of the fuels in the spent fuel pool. And this is a survey map. I was called from METI, Ministry of Trade, Industry, Economy, Trade and Industry in April 6th of 2011. And I was showing these pictures. And this is a survey map around these units. And you can observe that there are very high radio activities, for example, 10 or 20, 40 or 100 millisievert per hour. But after several months, the radiation level was much reduced. And basically now, in most areas, the radiation level is less than 2 millisievert per hour. And I'd like to show the location of Fukushima. So it is located 227 kilometers north from Tokyo. And the contaminated area is very much localized. And this is radiation levels. And this is radiation levels in April 2011. But 3 months later, it decreased like this. And in February 2012, much decreased. And nowadays, so red portion of this map is much decreased, as you can see. And this is the basic structure of this nuclear power plant. And it is composed of reactor building and the turbine buildings. So in the reactor buildings, there are 3 boundaries. The primary boundary is the pressure vessels. This is the reactor itself. And the second boundary is the containment vessels. And there is also a structure called the suppression chamber in underground level. And there is a reactor buildings. There are triple boundaries to cover the fuels. But all these boundaries were broken by the hydrogen explosion in this accident. And this is the ground level. This is the first floor. There are many entrances to enter this building. And this is a 5th floor. It is called operation floor. It is a very important floor where you can access the nuclear fuels from this floor. And there is a pool called spent fuel pool here. And we have also some nuclear fuels inside of this pool. And this is a situation of 4 units. And all the nuclear fuels inside of the reactors are considered meltdown. And there are also some spent fuels in the pools, and all the red parts are fuels. We should extract all the fuels. And also another biggest issue is there are lots of leakages. So we just inject waters to cool the reactor down. But this kind of contaminated water leaked so much. And another issue is that we should fix this leakage. And this is just the current situations. Now, Unit 1 is covered by some coverage. And this is Unit 2, and this is Unit 3. So we removed already the debris on the operation floor. And Unit 4, we removed also all the debris on the operation floor, and we already extracted the fuels in the spent fuel pool, 70% of the fuel. And all the fuels inside of reactors are considered meltdown, and there are lots of contaminated water in the underground levels. That is the situation. Okay, so just after the accident, the Japanese government and the TEPCO company, Tokyo Electric Power Company, which owned this nuclear power plant, established several special project teams. And one of the team was remote control and robotics team, and I was a member of this team. And after the accident, they released this kind of roadmap. Step 1 is for 3 months, and step 2 is for 1 year until the end of 2011, and then midterm issues. So here are some issues to be solved. cooling reactors or cooling spent fuel pool or mitigation of accumulated water and groundwater, or the monitoring and decontamination or countermeasures for aftershocks and so on. So if you look at these kind of missions precisely, there are lots of missions which are very difficult to be done by human workers. So we should introduce robot technologies or remote-controlled machines for these missions, such as the remote-controlled injection operation or removal of debris and so on. Okay, then after we establish the stable cooling situations, they released the new roadmap. And step one is defined as a period to start of the fuel removal from the spent fuel pool. It is estimated within 2 years. And phase two is defined as a period to start the fuel debris removal. And it is considered that it will take about 10 years. And after that, phase three, it is for the final decommissioning. And it is considered that it will take about 30 or 40 years. Actually, I'm now 55 years old, so if it takes about 40 years, I could be 95 years old. I'm not sure I can survive until the end of this decommissioning mission. Okay, then this is a kind of list of needs of the robots. And missions, the stabilization of cooling systems, or containment, including coverage of reactor buildings, or decommissioning. This is the final target, including extraction of nuclear fuels. And also, this is very important, reduction of radiation exposure of workers. For more detailed tasks, debris removal, or surveillance and mapping outside and inside of the buildings, taking images or measuring radiation and so on, and also instrument setup, sampling of dusts or contaminated water or fuel debris, and shield and decontamination and material transportation or construction of pipes, equipment, and so on. After the accident, we gathered, the scientists and engineers of robotics gathered, and we discussed how we can contribute to this accident. And Professor Yoshihiko Nakamura of the University of Tokyo called, and I was appointed as the chairman of this task force. And the task force is called ROBOTAD, Robotics Task Force for Anti-Disasters. So the objective is to propose and introduce solutions for disaster response and measures by applying robot technologies. But the most important discussion we made, one is discuss how tolerant the current robot technologies are for this decommissioning mission. And we tested all the mechanical parts and the electrical parts of the robot, and we found that it is tolerant until 150 or 60 sievert dose. So at that time, they were using the robot in the environment with about 20 millisievert per hour. So we just released some kind of assessment that you can use this kind of robot more than maybe 1,000 hours. So another issue was whether we can use a radio communication system for teleoperation or not. And Professor Tadokoro of Tohoku University and also Professor Koyanagi of Chiba Institute of Technology tested the wireless communication in different nuclear facilities, which is Hamaoka nuclear power plant. And they found that you cannot use the wireless communication because inside of the nuclear power plant, there are lots of walls and corridors and also obstacles, and it is very difficult to use the radio communications. So we just released this kind of assessment to the Japanese government and also TEPCO companies. And from here, I can introduce you some equipment we introduced so far. The first machine is the concrete pump truck. So the first requirement was to cooling down the reactors. So we put the lighting system and the camera on the top of the boom of a concrete pumping truck, and in the remote side, we monitor the image taken by this camera and remote control this boom to establish the stable injection of the water to the reactors. And another story is introduction of unmanned construction system for debris cleaning up. So there were lots of debris scattered in the areas. So some of the debris are generated by the tsunami, but another types of debris generated was by the hydrogen explosion. And this kind of debris was highly radioactive, and it was very dangerous. So the workers cannot approach to this kind of debris. So that's why we introduced this kind of systems. And you can see that we introduced many kinds of construction machines like backhoes or with iron fork or crawler dumps and so on. And all these kind of machines are teleoperated by radio communications. And it took about 7 months to clear up all the debris scattered in these areas. And after that, the radiation level of this area was much reduced. I'd like to introduce these technologies especially. So originally, this technology for unmanned construction system was introduced in 1993. We had a disaster of volcano explosion in 1991, and many people were killed by this kind of pyroclastic flow or avalanche of earth and rocks. So there was a requirement to make some kind of constructions to reduce the damage. But the volcano was still active and there was a risk. So that's why we decided to introduce this kind of technologies. All these kind of construction machines are teleoperated. And the important point is that this construction is still done even now. So it continued to be used more than 20 years. So the reason why we can introduce this kind of technologies to the nuclear power plant in Fukushima immediately was that this was still used in the site. It is a very important point when we think about how we can realize very practical systems which can be used in case of emergency. And then unmanned aerial vehicles, T-Hawk, was introduced in April of 2011. This is a product of Honeywell Company of the United States, and it was used for the inspection of the reactor buildings. And then PackBot, this is also the product of iRobot Company of the United States, were introduced for investigation inside of the nuclear reactor buildings. And this is the first time we could see what happened inside of reactor buildings. And JAEA, Japan Atomic Energy Agency, developed this kind of operation vehicles. So some kind of robots were teleoperated from these vehicles. And they mounted the gamma camera, and they monitored the radiation distribution also. So if you use the gamma cameras, you can take this kind of images, 2D images. So like thermography, you can easily find where is the high radioactive location. It is very useful information. And many other robots are also introduced for the debris removal inside of reactor buildings, like Talon, Bobcat. These are the product of Kinetic Company of the United States. And the Brock robot, this is a Swedish product. And then a Japanese robot called Quince was introduced in June of 2011. And this robot was originally developed for disaster response. And this robot has a very high mobility, even running on the terrain or debris. This robot can go downstairs, upstairs. And so that's why the TEPCO company decided to use it for the missions underground level, or second floor, or third floor, or higher floors. And the first mission was sampling of contaminated water and setting up water level gauge in the underground levels. And this is a photo of the modified Quince. They put many devices on the robot, and you cannot use the radio communication, so they mounted some kind of devices for wired communications. But the first mission was in failure. So they made a test with such kind of mock-up systems. So they construct this kind of simulated environment, and they test the robot and made the operator training. But the environment of the real facility, the width of the stairs was much smaller than we expected. That's why our mission was failed. But this robot was very useful, so it was used to other missions. For example, investigation inside of reactor buildings in higher floors. And in October 2011, the Quince succeeded in investigation of the operation floor. So it climbed up all the stairs, and finally it reached to the operation floor. And this is the interface, user interface display during the operation. So you can see the camera image of front camera and rear camera and overhead cameras. And you can also monitor the radiation levels. And this is battery, and you can have the image of the pose of robot. And this robot succeeded in the mission for investigation of fifth floor. But on the way back, there was some kind of failure happened. We considered that there was a failure in communication, and we could not communicate with the robot when he reached on the third floor. And this robot still remained in third floor of the Unit 2. So far, we lost 5 kinds of robot. This is one of the robot we could not recover. And also, we used a Warrior robot for cleaning inside of reactor buildings for the decontamination, but it was not so efficient. And the biggest contribution of the robot is the inspection of soundness of CS system. CS is core spray system. To realize the stable cooling functions, so we'd like to restart the core spray system. And if you restart these systems, you can spray the waters inside of the pressure vessels. So, but you should check all the pipes and valves and so on. And this kind of robots were used for the checking. And after that, we succeeded in restart the cooling down system. And it was very, very important issue. And then this is another story. This is inspection inside the reactor buildings in Unit 3. And so this is a mission. So this is a wall of the reactor building, and this is a wall of the containment vessels. If you try to access inside of the containment vessels, you should access this area and open this hatch. And so before that, we investigated the radiation level of these areas by robot. And this is a result. In the case of point 1, you can see that this is very high value, 870 millisievert per hour. So after that, they gave up to access this area. And but we'd like to observe inside of the containment vessel. So we introduced industrial endoscope to the containment vessels. There is some small hole which is called the penetration, and we inserted the endoscope from that hole. So this is an image taken by this endoscope. So you can see the water drops. That is injected water for cooling down. But you can also see many, many small noises. We consider that these noises are generated by the radiation. And in March 2012, and the radiation level was also monitored, and it was found that inside of the containment vessels, 73 sievert per hour was observed. So it is very high. You cannot survive more than 5 minutes. And another story is that introduction of ROV, so remote operated vehicles for investigating the spent fuel pool. There are lots of debris scattered on the rack of the fuels. And they use this kind of robot to make this kind of map of the debris on the racks. And after making this kind of a rack, they extract all the debris one by one. And finally, they started to extract the fuel itself. And this is another robot introduced in April 2012. This is called Survey Runner, produced by Topi Industry of Japan. And it was used for check the leakages underground. So they suspect some leakages on this kind of flange. And this robot walked along this kind of grating corridor, but they couldn't find the leakages at this time. Actually, this is one of the robots we could not recover also. Actually, there are several reasons why this kind of failure happened. There are three main factors. One is that we don't know the exact environment information. So we should operate the robot in unknown environment. That is one of the factors we could fail. And another reason is that all the robot is just a prototype. It was mostly developed immediately. And so the reliability is not so high. The third factor is human factors. So we usually make a test and train the operators by mock-up systems. But still, in the real situations, there are some human mistakes and misoperation of the robot, and sometimes it fails. Okay, this is another story. So they use this kind of remote-controlled crane or construction machines to clear up all the debris on the operation floor. And this is another story that they introduced this kind of balloon systems to investigate in the operation floor of Unit 1. So it is covered by the coverage, so it is very difficult to access this operation floor in the case of Unit 1. So there is this kind of equipment hatch. So we utilize this kind of hatch and just introduce this kind of balloons. After several failures, we finally succeeded in introduce kind of the balloon and take some pictures. I'm sorry that this was a movie, but it didn't work. Okay, and this is the quadrupt robot developed by Toshiba company. It was used for the inspection of suppression chamber vent pipe leakages. And this is a combination of parent robot and child robot. And this is child robot, and this robot was released from this parent robot. And this robot walks along this pipe and approaches to the connection part of the pipes and check the leakages. And there are also some failures in this type of robot. Once the robot fell down, and also once the small robot could not operate. But after experienced some failures, finally we succeeded in check all the 8 pipes. But even in this time, we could not find any leakages. And this is another story. So Flygo MA, a robot which was developed by Mitsubishi Electric Toki Systems, was introduced for inspection in some areas. And this robot was developed by Honda company and AIST, National Institute of Advanced Industrial Science and Technologies. And this manipulator has 11 degrees of freedom. And Honda developed this manipulator by utilizing the Asima robot technologies. And AIST developed this kind of mobile platform. And there are lots of places in high locations to be checked. But we introduced this robot in June 2013, and now it is still working on the site. And the Kajima Corporation established this kind of automated system for debris transportations. So it is a combination of 2 systems. So one is automatic transportation by a crawler dumps truck. This truck transports debris from the debris destruction site to the temporary storage facility. And second system is the automatic transportation by forklift. And this forklift is automated to transport the debris from this storage to the final storage. And this is a robot called Asako Sora, developed by Hitachi Engineering and Services. This is very small construction machines, but this robot has dual arm. It is very useful if you have two arms. And you can make a very, dexterous manipulation, for example, for removing the debris. And this is also a dual-arm robot, which was developed by Mitsubishi Heavy Industry. This robot was called Meister. And this robot was introduced recently for core sampling of the operation floor. And in November last year, we finally found the leakage of contaminated water. So it took more than 2.5 years after the accident. So Hitachi AG Nuclear Energy Company developed this kind of boat-type robot, supervised by Professor Tamaki Ura of the University of Tokyo. He moved to Kyushu Institute of Technology recently. And this robot was introduced to these areas. So this is a suppression chamber, and this room was called the Taurus room, and there is some contaminated water. And they put this robot on the surface of this contaminated water, and it navigates 180 degrees. Actually, the suppression chamber is a kind of structure of torus, donut. And this robot navigates itself to this clockwise 180 degrees and also counterclockwise 180 degrees. And at that time, this robot found some leakages from the broken pipes and also some water flow along the walls of the containment vessel. And this robot was called Raccoon, and it was developed by Atox Company of Japan. It was also introduced for decontamination. And another decontamination robot was Moose, which is a product of Pentec Company of the United States. And there are several types with dozer or vacuumer or scabra and so on. It was introduced for the decontamination of the operation floor of Unit 3. Okay, then another type of robot was developed and introduced for measuring the water level inside of the suppression chamber. This device has sonar systems to measure the level of the water inside of the suppression chamber. So when we firstly we introduced this robot, but it was failed because the contaminated water was much oily and turbid than we expected. So we changed some of the ways to measure and re-enter this robot. And finally, it succeeded to measure the height of the water. And this is rather recent results. So recently we succeeded in introduce some radio communication systems. So we usually use two robots, and one robot is used for the relay system of radio communication. And this is a combination of the Warrior and the Packbot. And actually the gamma camera is very heavy, and it is only mounted on the Warrior robot. And in this case, Warrior robot investigated the radiation distribution. And January this year, Asako Sora found this kind of contaminated water flow by accident. It was used for the debris clearing, debris removal, but by accident it found this kind of water flow. We are very, very surprised. And now we are checking the origin of this water. And then this is the most recent utilization of the robot. And the mission was to take the core samples of the operation floor. The mission was very difficult. And this is Unit 2, and it was not, the building was not broken. But there was a kind of window, and we introduced a robot from this window and to take these kind of core samples. But there are some fences, so you should remove this fence first by this robot. And when we introduced this robot, it succeeded in taking over this fence. But when it reaches to this area, there was a ditch, unexpected ditch on the floor, and it fell down, and we couldn't recover this robot. But after that, we introduced another type, robot Meister, to this mission, and finally it succeeded in taking the core sample of this location. So I talked about a long history, and also this kind of robot was also introduced to check the leakages of this pipe, and it found some leakages of this kind of barrels, and it was very successful. And I'd like to introduce some robots under development. And this is a robot called the Transformer. It is very different from the Transformer you know. And we should introduce the robot from the very small hole called the penetration. But this robot should navigate along this kind of grating floor to access this kind of area, which is called pedestal. So there should be some meltdown fields here, so we'd like to see it. But the entrance is very small. So when we enter this robot, the shape of the robot could be some kind of snake shape. But it transforms itself and becomes this kind of shape when it is navigated here. And it will be introduced very soon, I think. And these are some other robots under development. They are developed by Hitachi Nuclear Energy, underwater ROV, underwater wall climbing robot. Or this is some other robots developed by Toshiba and IHI company. And this is inspection robot for lower wall, suppression chamber, bent tube junction, and so on. Okay. So, and the aerial vehicles are also under development to be used inside of the reactor buildings. And one is developed by Chiba University and Atox company, and also IRS. This is International Rescue System Institute and Tohoku University with collaboration with Carnegie Mellon University. Okay, there was also another project which is called Unmanned Disaster Response System Research and Development. And it is funded by METI and NIDO. And these kind of robots were already developed, including radio communication repeaters or common human interface or robot suits for the workers. And some of the systems were already introduced in real sites. Okay, and I'd like to introduce some interesting technologies. So this was developed by Professor Yamashita, my associate professor. It is a kind of human interface. And he put the 4 fisheye cameras on the robot, and this is the camera image you can take. Actually, the fisheye camera has a very wide range, so you can take the very wide area information. And you can combine the image, integrate the image to generate image taken from the virtual camera on the top. And this is a result. So you can generate this kind of image even if you don't have the camera on the top. So it is very useful when you operate the robot in very narrow space or such kind of maze environment, as you see. And also, we can superimpose the information taken by the laser range sensors, and you can easily recognize the obstacles. And it will help the teleoperation of the robot. And recently, they succeeded in generating this kind of view from arbitrary viewpoint. By integrating the 4 images of fisheye camera, you can generate this kind of view. So you can see the images of surrounded area of the robot, and you can also recognize some people in the environment. And we think that it is very useful for teleoperated robot inside of reactor buildings. Okay, so then I moved to the stories for the decommissioning. So this is a main story planned in TEPCO companies. So it is a long story. So firstly, we introduced some robot system for decontamination, reduce the radiation levels inside of the buildings. And then we introduced some equipment, robots, to localize the leakages and fix it. And then we try to fill some water in the containment vessels for the shielding the radiation from the fuel debris. And of course, we should fix all the damages of the pipes, of the valves, and so on. Finally, we'd like to fill water fully in the containment vessel. Then we introduce some kind of special devices to cut and extract the fuel debris. And it is the original plan. But now we are thinking it is very, very difficult missions because we should check more than 700 valves and pipes, and there are a lot of possibilities that some parts are broken. Okay. Okay. So, and this is for debris extraction and decommissioning. So actually, we should develop many kinds of the robot, and we should have some portfolio of the robot and equipment, because there are many kinds of tasks and the environment. And also, from now, we need to access to the fuel debris. We need some manipulator or handling devices. And also, we are approaching to the debris, the radiation level will go up dramatically. So we need some more radio-tolerant devices. And also, we should think about alternative plan, for example, operation in dry conditions. So, considerations. Okay, actually, we failed to introduce the robots technologies immediately after the accident. Of course, nowadays, it's okay, we introduce many robot technologies. But just after the accident, Japanese media criticized robotic scientists. And they indicated the responsibility of robot scientists. And there are a lot of emails sent to the Honda company asking why Asimo cannot be used at the disaster sites. And Honda company apologized that the function of Asimo is not enough for the disaster response. And people are very much disappointed to know the robot technology is not so useful in real situations when it is demanded. So that is a problem. And actually, we have many projects for the nuclear facilities. We develop many kinds of the robots for nuclear facilities, but they are all limited to basic research and fundamental technology development. It is not so practical. And also, after the JCO criticality accident, they developed many kinds of robots, but it was not maintained, so we could not use it. So that was a big issue. So we had lots of robot technology R&D projects for nuclear applications and disaster response in the past, but we failed in introducing the robot technology smoothly. So there should be some kind of gap between expectation to robot technology and reality. So that is a problem. And so these are some lessons learned and future issues. First, we should examine the political strategies. We should think about sustainability of technology for possible disasters and also limitation of demand and market, because disasters don't happen so often. So actually, the demand and the market are quite limited. That is another problem. And we should combine with maintenance use. And we recognize the necessity of projects to develop more practical technology usable at sites involving users. So these are some, we proposed some projects. For example, technology mobility for mobility and access in extreme environment, or technology for stable communication, technology for spatial awareness in remote control, technology for autonomy to facilitate remote operation, and sensing technology for inspection, diagnosis, maintenance, so on. And also we propose to start project for system integrations, including challenge or competition for solution derivations. Then we recognize also the necessity of facility and organization for practical technology development, testing, and quick response to possible emergency and disasters. And it is also necessary to conserve the technology and knowledge for long-life artificial systems. Okay, this is a story we proposed with the industry to the Japanese government. So there are some needs for decommissioning of nuclear power plant, but we should also prepare for the possible nuclear accident for the future. And also we should think about preparation for natural disasters and accident of social infrastructure such as tunnels or bridges or chemical plants or complexes. So there are many difficult factors in tasks and environment for humans. So that's why we need to utilize the robot technologies. We should also think about the productivity improvement of monitoring or inspection or maintenance. So we propose two things. One is development and measurement of practical RT systems, and another one is preparation of the system deployment in the case of emergency. Okay, this is, we propose three things. One is project and program for RT systems, R&D. And second one is very important. We propose to establish RT Center for Disaster Prevention and Response. This center should have some function for operation test and operator training, functional evaluation and certification, and manage of technological information of RT, including archive and database, and emergency response with device development and operations. So utilization in ordinary situation is very important if you utilize it in emergency situation. These are some political proposals, strategy planning and standardization of evaluation of function and regulation design and so on. Finally, I will introduce some secret. So how I behave to propose to the Japanese government. So I made 3 scenarios. One is decommissioning, and social resilience is another one. And the third is reconstructions. I put the industries in the center of this mission and make academia a kind of support of the industries. And the first scenario is decommissioning. TEPCO is responsible for decommissioning, and the Japanese government is supporting. And Agency of Natural Resources and Energy should fund for R&D, and industry should make research and development with academia, and the outcome should be fed back to the TEPCO. This is the first story. Second story, we generalized this concept for preparation of disasters. So METI and MEX, this is Ministry of Economy, Trade and Industry, and the Ministry of Education, of Science and Technology fund for R&D of robot technologies. And the industry and academia developed the robot technology, and users are some public sectors, not private sectors. So it is Ministry of Land, Infrastructure, Transport, and the Ministry of Defense, and the Fire Defense Agency. And the third story is risk constructions. This outcome should contribute to the national safe and secure life. And the third story is reconstruction. Reconstruction Agency of Japan is responsible for reconstruct the Fukushima area. They should support the local government. And it will contribute to the economy and life of local area and communities. So we put some, this international disaster response robot R&D center and the international disaster response robot testing facilities to be established in Fukushima areas. So all the results should be tested there, and with some support of local industry, and the result is tested and introduced to them. So I integrate all the 3 stories. And finally, many kinds of projects are now started in Japan. I don't have much time, so I skip all the one. But my image is now under realizations. So I think it is a very good chance to collaborate with internationally to realize this kind of framework. Okay, I'm sorry, I will summarize. This is the last slide. For future, I think it's very important to transform the beta experience to the chance of the technological advancement by developing more dependable and demanded technology for safe and secure society. And second, I think it is very important to construct international network and framework for cooperation in knowledge sharing and technology transfer. And last, it is also very important to develop young human resources and keep knowledge and technology beyond the generation. Thank you very much for your attention.
Well, thank you very much to Professor Asama. I have very light duty, which is really to wish you well this evening and for the rest of the Congress. Thank you very much.